Hi, I'm Natalya Tatarchuk, and I'm a Distinguished Technical Fellow in VP, AAA and Graphics Innovation Group. I've recently switched gears to lead our new Graphics Innovation Group. Prior to that, I've led Unity's graphics team. Today, we're going to talk to you about Unity's rendering architecture and its evolution. By understanding what our engine's goals are, we can help ground our architecture design principles in the context of solving the right problems. So we'll go through that first. Then we'll deep dive into the scriptable render pipeline architecture, or SRP for short, and how we are evolving it toward higher throughput with the hybrid dots SRP architecture, where we extend the SRP architecture to operate on both Unity's current game object runtime, as well as the new data-oriented tech stack. Let's take a look at what our engine is trying to do and why first. At its heart, Unity is about empowering creators. But what kind of creators and creations are we trying to empower? What does it actually mean for our architecture? Artists have created visually and emotionally stunning pieces with Unity for a decade and a half, because our engine gives them the freedom of expression in terms of creativity, style, visuals. And thus, one of our major goals for our rendering architecture is to give the creators maximum freedom for their creative vision. You could make something 2D, 3D, cel-shaded, realistic, cartoon, it's a long list. Most people create entertainment so that it can be experienced by someone, so that it can be shared. Reaching a wide audience matters, both to share the stories, but also, pragmatically, to be successful. Now, to help reach the widest audience, we support over 20 platforms, with the goal of making it as easy as possible to target multiple platforms concurrently. Of course, for us, this means that our techniques must work on all these platforms in some way. No small feat. It's important to us that creators have the ability to make a project that can run performantly, from low end to high end. This means that the tools in our toolbox need to either scale themselves or have steps that make sense at different hardware tiers and types. The interesting thing is that even if you slice through one tier of hardware, it's a deeply fragmented world. Zoom in on the Android OS, and this is the landscape. Thousands of mobile devices which vary in hardware capabilities, as well as APIs. It's complex to test, optimize, and target your game to these devices. Our goal is to make it as easy as possible, architecturally and in terms of content creation, for the creator to do so without having to burden with all of this complexity directly. We talked about games so far, and it's easy to keep thinking of Unity as purely a game engine. Certainly that's where we are rooted, yet we're not building a game engine only, but also a larger generalized framework for application creation. We support anything from 10 kilobyte applications, instant games, or embedded apps running on the latest fridges, for example, to mobile, console, and PC games, to AR and VR experiences and applications, to hundreds of terabytes cloud streaming industrial and automotive solutions. All of these use cases come with their constraints and architecture demands. For example, with Unity Forma, we need to have the same runtime customizable high-fidelity design asset run smoothly on the high-end platforms as well as on smartphones at full quality and interactivity. Another example is Unity Reflect product, which ingests large industrial CAD data directly in the player on the client. We have to performantly render this huge data set, up to hundreds of terabytes, with no pre-baking. Can't build Umbratones for visibility calling, for example, at interactive rate on our full range of platforms. We want very low friction from idea to implementation for developers on our architecture, with all the necessary tools provided by default, but allow for quick and easy tuning as needed, whether a simple surface level change or a deep surgery. For example, the creators of Ori and the Will of the Wisp, a breathtaking and beautiful game, had such different needs for the look of the game, they created their custom rendering pipeline in SRP. This would be very challenging without the flexibility of SRP's architecture, though we're still in the process of making this easier going forward. Customizability can often mean easy to change, but we need to think about extensibility as build on top while providing a stable base. For us, this especially comes into play when thinking about our asset store ecosystem, with many thousands of assets and plugins that creators develop on top of our engine. Sustaining this ecosystem is an important requirement for our architecture. Extracting from these engine goals, then the key principles for architecture are platform reach, deep flexibility and customization, performance across the gamut of platforms supported, quick iteration to unshackle the creativity, both for development and creation, and continuity. Keep existing content working or upgrade it smoothly. Next, let's take a look at how our architecture evolved to answer these goals. We've started with the built-in render pipeline, moving to the scriptable render pipeline SRP architecture, and our latest evolution, the hybrid dots SRP. Note that the hybrid architecture does not support built-in, as built-in only supports the game object runtime. Built-in render pipeline was our one-stop-shop turnkey solution for all supported platforms, with forward and deferred pipelines and a solid mix of graphics features. Users found it very convenient and easy to use. Yet it was simple to run into major challenges with this architecture. With its black box system, the configurations were hard-coded for the hardware in the C++ land and not easily modifiable. And while built-in render pipeline offered a turnkey solutions, it also locked the rendering algorithm in a way that often didn't provide best performance for a given platform. It yielded sort of lowest common denominator to keep up with the cross-compatibility needs. And with each addition of new platforms or hardware stages or APIs, the cost of modifying this architecture continued to increase exponentially, making it fragile and hard to maintain. Its flexibility was also a challenge. It exposed a large amount of user-led callbacks, allowing changes or injection of state at any point in the frame dynamically by calling to C#. Would you like to switch your object from rigid to skin? Go for it. Do you want to change decal blending mode late in the frame? Totally fine. This made it very challenging to cache data effectively and to manage persistent state intelligently. And this was at the heart of many performance issues for this architecture. Yet, while it's tempting to scream, do away with it with fire, it's also incredibly important to realize how much this flexibility offered the very advantage of Unity. The lack of shackles, which easily enabled powerful prototyping and creativity. These hard-to-optimize for choices might seem very bad, but they also enabled Unity Engine to be an amazing place of creativity. And our goal for the architecture evolution is to learn from this and to preserve as much of the power and the freedom as possible, while also finding new ways to better understand creators' intent and smartly convert it to perform in runtime. That is the really hard problem to solve, but also the most interesting one. So it's clear the built-in render pipeline wasn't going to fit our users' needs. How did we evolve forward? Let's say we wish to write new physically based material model with changes to the material shaders and gbuffer layout, plus lighting in our engine. How does that flow through the engine layers? We probably need to iterate on the shader passes, render texture layout, and so forth. The heart and soul of the algorithm, this is where we want to spend our time as graphics developers, not boilerplate code in the later layers below. Typically, when we're working with game engine systems, we're operating in C++. For graphics, we frequently also do work using shader domain-specific languages, which mostly deal with the higher elements of the stack. Occasionally, though, when shaders have very specific hardware dependencies, VRS, instancing, tessellation, async compute, they need to reach out to the engine or low-level API layers and may require deeper changes, in line with the corresponding shader changes. This should be an infrequent operations though, mostly during bring-up of new hardware or API layers. In C++ land, we iterate via familiar build plus link and continue experience. Of course, distributed build helps with their iteration time there, but we're still limited by the serialized link pane. And the workflow of rebuilding the executable also means the inconvenience of quitting the game level, restarting it, all in an effort to get to the same place in the frame I was trying to debug in the first place. Pretty tedious. Now, what if there's a different way to iterate as a graphics developer? We can see that to keep up with the platform's use cases, variety, and product needs, a modern third-party game engine needs to be highly configurable. It needs to react dynamically to varied throughput and make intelligent choices about platform constraints. But we need to rethink how we design it. How can the previous observations help us find a philosophical shift for our design? Learning from the challenges of built-in render pipeline and wishing to have a better iteration experience in the C++ land, we designed the SRP architecture to be user-centric. It controls rendering from C#, easy to modify and debug. The engine executable makes no assumptions about the underlying rendering pipelines, forward or deferred, tiled or not, ray tracing or rasterized or hybrid, G-buffer layout, or whether there is even a G-buffer to begin with. These are all explicit pipeline design choices that happen in C# and shader level. It's highly configurable with an inspectable open API so that you can write your own renderer if you want to do that or extend as needed. It's lean. Take only what you want, only when you need for your platform and project in mind. Of course, since our aim is to create amazing games of real-time experiences, performance of our architecture is critical. No amount of flexibility and generalization will make that a non-requirement for us. So the technical goals for the architecture are: componentize the steps of rendering via concepts of building blocks you can put together, customize or extend, separate control of rendering order from the high-throughput inner loop execution, and last but not least, since we've moved majority of iterative algorithm development into C# and shaders, we can reap the benefits of quick iteration with hot reload and parameter changes. That's one of my favorite parts personally. With SRP, low-level engine still stays in C++ land as before. This is our high-throughput performance-critical layers. But we've moved some of the functionality for controlling render passes and game-based rendering into C#. Of course, the shader programming is still present, but shaders mostly need to agree just with the C# layers, with the exception of high-throughput instance data, which is still provided by C++ for performance reason. The interface is designed such that you invoke a calling operation on the scene graph, followed by a draw on the resultant list of scene nodes, specifying specific shader passes to draw with. Under the hood, the engine will call the scene graph in a jobified way and identify nodes that pass the calling and drawing parameters that are passed into the C++ low-level render architecture. Shaders can be designed for a particular render pipeline in mind. And now that we understand all the components on the high level, it may seem like we just talked about creating a bunch of Legos for devs to use. So this is a good time to think about Legos for a second. If we look at the Lego group, over the years they've reached a large number of audiences, with many of their customers having different personas, age, needs. But there are two categories that are very clear. Lego Classic. This is their main offering for all audiences. Kids can understand and play with it, even adults can enjoy playing with it. It provides the flexibility and freedom and creativity. You can build anything you want, but you don't have the perfect pieces that aren't part of the main building blocks to craft something very fine-tuned. On the other hand, there's Lego Technic. This one targets an experienced Lego builder. These are the state-of-the-art Lego products for the perfectionists. The Bugatti here has the perfect curves and shapes from the custom Lego pieces designed specifically for the vehicle. Yet, you get what you get. Your customizability is limited to what's in the box. You can't build a great helicopter with the Bugatti pieces. The Lego analogy fits how we think about the starting places for Unity's render pipelines. We ship with two render pipelines out of the box, one that provides maximal platform reach and customizability, the Universal Render Pipeline or URP, and one that strives for photorealism and high-fidelity graphics, but that reaches a more constrained set of platforms, the High-Definition Render Pipeline or HDRP. Of course, both of these are user-land customizable. Anyone can reuse existing functionality and change and adapt parts of the pipelines that they need to modify. For the hardcore, there's also the path of building a completely custom pipeline from scratch. So in the Lego terminology, URP is the Lego Classic. It's accessible, the barrier to entry for developers is lower, you have the maximum flexibility to build the type of visuals that you're after, and reach your audience on as many platforms possible and build beautiful creations with great performance. Yet, if you're seeking the bleeding edge, you may have some limitations toward perfection. We think of URP as the powerful successor to the built-in render pipeline. designed to be the default rendering for Unity for authoring beautiful 2D and 3D graphics and deploying everywhere. SRP supports the vast majority of Unity's platforms, and it can be used for a variety of examples: 3D, 2D, forward or deferred, and many more. Now, SRP's Lego Technic is designed for the perfectionist to achieve that state-of-the-art high-end look, photorealistic or stylized but physically based in all cases, that you would see in a AAA or offline rendering with bleeding-edge graphics. It ships with a rich feature set: material models, lighting, shadows, volumetric, scalability settings, ray tracing, but a constrained set of customization options, which is constrained due to console GPU performance optimization. SRP has been optimized for maximum performance on GPU compute-capable platforms such as these here, and here are some of the examples of what SRP is capable of. So with this, I'd like to hand this over to Tim Cooper, who will tell you more about how we designed the scriptable render pipeline architecture.
Hi, I'm Tim, Director of the Graphics Foundation team at Unity, and I'm going to talk today about our journey from a fixed black box style rendering technology to a much more flexible and customizable architecture called the scriptable render pipeline. We will be taking a look at different parts of the Unity rendering architecture today, covering parts of the asset interface, our graphics backends, and the SRP API that both HDRP and URP utilize for their rendering. The asset layer is the front-end user data interface into rendering. This is the space where content created by artists and similar is injected into the renderer. The SRP front-end is a scripting layer that lives in userland, where you can customize your rendering. This is where you would write your rendering flow or processing, and is the layer where URP and HDRP are implemented. The graphics backend is where all of our core rendering lives: batching, graphics device interaction, and other parts of our performance-sensitive code. This layer consumes the authored asset data by processing instructions injected from the SRP frontend. We will cover all of these layers, but the SRP API is what allows the SRP technology to be what it is: flexible, fast, and configurable. Contrasting our previous rendering technology, we really wanted to play to the strengths our users see in Unity and extend those strengths into userland rendering. That is, customizability, easy-to-use interfaces, and simple-to-understand asset abstractions. Let's talk about the architecture of the SRP. One big design fundamental for our SRP abstraction is that it's built to use many existing Unity workflows and concepts. With that in mind, let's take a look at the primary building blocks that content authors work with in Unity. Jumping back to our architecture, you can see there is a block here for assets. This is a stand-in for any user-authored data type that is consumed by the SRPs, and we have various content authoring workflows in Unity to construct this data. If we start from this perspective, you can see that we still use the same material, mesh, texture, and shader object that were used in the previous rendering technologies in Unity. The contents of the shader might be different: pass names, constant buffer layout, algorithms, but the actual data types are the same. What's exciting here for our technologies is that we are utilizing existing constructs for our data interface into rendering. A material in SRP Unity is still just a Unity material. This provides Unity users with a way to upgrade their existing projects into the new technology by either replacing the data in place or running an upgrade process. For both URP and HDRP, we wrote upgrade scripts to convert built-in content to the newer rendering pipelines. In the end, most of these asset types are just data containers with some algorithmic smarts and front-end tooling around the outside of them. When it gets to the rendering portion of Unity, we mostly just want to consume the settings as needed. For example, binding a texture for a draw call or setting a color in a constant buffer. One asset area I want to cover in a little more detail is our material and shader system, as this is a big area when you're customizing rendering. Our shader object is essentially an interface which contains a block of properties such as colors, textures, vectors, and a number of name passes containing HLSL that can then use these properties. Our material object is essentially a configuration of the shader object that contains the specific values for the data for these shader properties. In Unity, a shader is essentially an interface, and a material is a specific override of that interface with concrete properties. When performing rendering via the SRP API, you are required to specify the specific pass name you wish to draw. This is the connection between the SRP pipeline you write and the shader side of rendering. Now, how do we utilize these assets when it comes to rendering? These assets are data types that live in our graphics backend, which are then attached to nodes of our scene graph. This means we have access to them at rendering time. The core of the Unity engine is built in C++. This is where large parts of the runtime live. As a lot of the functionality you would associate with performance-sensitive rendering lives in this layer. Batching, graphics device interaction, threading, graphics jobs. Much of this portion of the engine is heavily OOP-based. This leads to some pointer soup and similar when performing rendering operations. Sebastian will talk about how we are improving this later. This is also the space where our scene graph lives, and many of the operations invoked on the SRP API trigger batch processing operations onto this scene graph. But I'm getting a little ahead of myself. What API do we have in SRP to interact with this graphics backend? We needed this drawing API to be as fast as possible. It was a strict requirement for us, and C# does not offer the performance we needed for per-node operations. We converged on a solution that allows for higher level rendering flow to be controlled from C#, but draws are just controlled as batches. Essentially, post-culling, we would have a list of all valid render nodes and be able to say, render the opaque ones front to back, or render the transparent ones back to front. This allows for rendering control flow to live in C# without drastically hurting our runtime performance. The API we arrived at for this was called the render context. This is a proxy object that lives within our C++ layer, but has a binding layer into C#. Holding this object allows access to our rendering API. Looking at this mock render pipeline implementation, you can see the granularity of operations that are possible on the context. Like I mentioned before, they are not super low level, but they provide a solid granularity for working with rendering algorithms. This is the lowest level of our exposed scaffolding, and on top of this is where we build many features like render graphs and similar. As we discover new requirements or receive feature requests, we extend this API to add new functionality. For us, this strikes the right balance between performance and usability and ties in well with the principles that we have established for our API design. On top of this C++ layer, we have our C# scripting layer, and this is where URP, HDRP, or a custom render pipeline can be implemented. This layer takes advantage of many of Unity's strengths as a development platform, specifically our ability for user code to be written in a sandbox away from the core engine. A crash in this code won't take down the whole engine, and the ability to leverage an existing well-known programming language, C#. We also have a number of utility tools that live in this space as well. And we use these tools to build big parts of URP and HDRP. We'll dive into some of them later and how we have approached the idea of scaffolding when we've built them. One other Unity advantage I wanted to highlight was due to the SRPs being built within the C# layer, it allows us to extensively modify rendering code without recompiling the whole engine. This is a really big one. We can change anything in that C# layer and not have to leave the Unity editor tool. This allows us to have really quick iteration time, and it allows us to experiment and prototype without feeling like Unity is getting in the way of our ideas. So as we have seen in Unity, we have two rendering pipelines targeted at different use cases. And as you can see, they both have very different high-level implementations and flow. One of our biggest challenges has been about how we can expose both the low-level rendering features as well as the high-level constructs in a way where they are usable for multiple render pipelines, including custom user pipelines. As I have touched on, we use the concept of scaffolding for the design of the majority of our features. That is, we have low-level raw APIs that you can use if you want direct access to rendering concepts, but we also have higher-level constructs built on top of these that are more usable but offer less direct control. To delve into these, we'll first need to understand how Unity renders a frame. To start with, current Unity is a heavily main thread focused engine due to its extensive C# callback-based player loop. The advantage of this is that Unity is very fast and easy to prototype with, really low friction from an idea to seeing it on frame. But this needs extra attention when you're looking to scale up a project and as they become more demanding. You need to ensure that you're offloading work manually to worker threads, and you're also playing nice with how a render thread and our main thread interact. A frame in Unity is built in a number of stages, and I'm using an example from the universal render pipeline here. To start with, there's the game logic section in the frame. This is where non-rendering systems and user script code is executed. And then we move on to the rendering phase, which will include culling, which includes userland code callbacks for visibility, performing the rendering algorithm itself. This is done on the main thread in userland script code. Next, submitting the operations, which include figuring out draw state, sorting, and any per object data. And finally, offloading the rendering command buffer to the render thread. Each phase of this rendering will offload parts of its work to worker threads, and this will scale in a variety of ways, depending on the content, the platform, and the project configuration. This highlighted section is the render call into the C# user layer. Let's dig in and see what happens here. A note on coloring, C++ layer code here is represented in green, and C# user code is represented in blue. You can see in this frame that we've called the URP render function. It will then call back into C++ for culling before processing the rest of the URP script portion, which is following in blue. So what is the workflow for our culling? Let's start with intent. We want to perform a lot of mathematically heavy operations in our scene graph and get a renderable set of nodes. This means we need to do this in a performant and parallelizable way. So we actually favor offloading our culling into C++ with a set of options that can be configured from our C# API. This is done by a call to context.cull. This will perform the culling operation and with whichever camera settings are passed in. Flags exist in this structure for things like occlusion, rendering layer filtering, and similar. We let this be configurable so users can customize the call to their own specific rendering needs. Whilst the culling itself is quite black box, it offers users a lot in terms of callbacks and ability to add custom code when things become visible or invisible. We have quite user-friendly workflows here. Essentially, each time a culling operation is called, we parse our scene graph and generate a list of renderable nodes that get wrapped into a culling result, opaque handle. Each time this operation happens, we issue visibility callbacks both to internal systems as well as C# script. These are often used to perform calculations that should only be done when an object becomes visible or invisible, things like skinning or similar. These at culling time callbacks have their pros and cons. They allow for same frame updates for visibility operations, but add slowdowns as we need to call individual user scripts attached to objects. Essentially, this is a sync point. The flexibility and ease of use in terms of this API has gotten a lot of Unity projects a long way, but this is one of the older systems in Unity and is an area with which we wish to improve in the future. For an engine like Unity, changes to systems like this can be difficult as we have to balance continued functionality of existing user projects with the desire to improve our technology. When we make changes to callbacks and similar, we need to be exceptionally careful to not break things or offer some mitigation strategies for our customers. After culling, you can then do the actual frame of rendering. The goal of this presentation is not to dive too deeply into the specifics of either HDRP or URP, but instead look at the shared rendering API both pipelines use. So how do both pipelines submit work? We've covered the rendering context earlier and how it performs batch processing on the returned render nodes from the culling operation, but how do we define those batches for rendering? When drawing with SRP, you need 4 things. The culling results, which we've already covered, a filter to filter these culling results. This will filter the render nodes with some additional rules for the draw call. Filtering is generally done on 2 parameters. There are a few more we offer as well. Anything like a user-assigned layer, which is a content authoring concept we have in Unity, where objects can live on layers. A render queue for the material. The render queue on a material will specify if the object is generally considered opaque or transparent or some other property. Third, when we wish to do the draw, we need a set of drawing settings, and this will determine how these objects are drawn. So for example, we need things like how the objects will be sorted for rendering. So for transparent, you'll want to specify a sorting flag for back to front, whereas opaque, you may do some other form of sorting, either front to back, or maybe some form of z-binning or batching based on materials. The specific shader pass to use for the shader that's attached to the render node, if the pass isn't present in that shader, this object will also be skipped for drawing. And third, any flags for per object specific data you wish to bind for the draw. So this could be things like binding the previous frame matrix if you're wanting to use motion vectors, any light probe data, if you want light per object light indices calculated and things like this. And finally, you wish to add this draw call to the context. And just to reinforce, like at this layer, SRP does not have access to the individual meshes, transforms, or render node. This allows us to set a broad phase operation for the drawing, and then we can perform backend specific batching operations and optimizations given the configuration that's been passed in. So in Unity, we have taken the approach of broad phase culling, then fine-grained filtering. To take, for example, this scene here, which has both transparent and opaque objects, being the windows and the panels. In Unity, culling would generally return all of these meshes as having passed visibility and being within view. We then use the draw filtering to select which ones get rendered for each draw renderers command. For us, this strikes a balance between performance and flexibility. It's often useful to have low-level access to the rendering context, but it's pretty raw and not fully feature-rich. Let's examine the SRP frontend, where we have most of our feature-rich tooling. We wanted to provide more functionality out of the box for people who are writing SRPs, and some good libraries would actually make this much easier for them to do the right thing. This serves us at Unity by giving us the tools we needed to build URP and HDRP, but it also helps users who are writing their own custom SRPs. On top of the render context in our C# layer is where we built this out. These tools have a focus on performance by default and ease of use. As you can see, we have a number of tools, but we're only going to look at a few today. Let's start by looking at our render pass. If you're familiar with mobile architectures, you'll know that they are generally tile-based renderers. A side effect of this is that they are very sensitive to resolving GPU memory back to main memory. That is, if you want to render to texture and then bind it as a texture for use as a read target in another pass, you need to read that back before you can bind it. It's a very bandwidth intensive and slow operation, and many mobile games suffer performance issues by not being able to stay on tile as much as possible. Many engine developers have tried porting tech to mobile without paying close attention to this and run into problems. We've even made this mistake a number of times when we've been moving technology to mobile. So we wanted to make this much easier to do and not end up on a bad path. So we developed a relatively easy to use userland render pass API to handle a lot of the backend here. The way this works for us is that on the context, you define when a render pass starts using the exposed API, along with the attachments that get used in the pass. For each subpass, you can then use these attachments how you would see fit. Here we have a simple deferred renderer where one pass fills a G buffer and the second pass performs a lighting pass. If you look at the shader code here on the right, you can see that we provide some macros for reading from these frame buffer inputs. On mobiles, these will become frame buffer fetch operations. And on devices that don't support this, like most PCs, we will behind the scenes bind this as a render texture for sampling. We provide one API that benefits mobiles heavily, but actually still functions well on other devices. This allows you to write the code once, but have good performance characteristics across the range of hardware that Unity supports. Render pass is great for situations where it's possible to stay on tile and share the same pixel data. But as we know, that's not all that's needed for rendering performance and memory management, as you'll often need to read from neighboring pixels, use a texture from a previous frame, or use a texture in a location quite far from its creation. There are a number of ways to manage this, such as manual texture management, some texture pooling classes, or similar. We wanted to be more explicit about tracking graphics resources across the frame, so we built a render graph that lives, once again, on top of our render context, but interacts with it. By using the render graph, it's possible for us to lower our high usage memory watermark and ensure that we are not using more memory than we need to within a frame. Our goal is to combine our frame graph and our render pass API to have the best of both worlds. And now we are back to our higher level. We use all these tools to build out a set of commands to inject into the render context. That is essentially the goal of the SRP script callback. It's to define the rendering flow. Now, To kick off the device submission, we need to call submit on the context. This allows the author of the render pipeline to control when work is kicked off. You can be smart about this to reduce bubbles and also to manage custom submission. When submit is called, we kick off a number of jobs and return control back to the main thread. These jobs execute the filter and build a list of nodes to render, then pass that down as consumables to our graphics device layer. You may notice that we have a large block of timeline here associated with the CPU cost of rendering. Sebastian will talk about how we have a new architecture here that reduces the processing due to having persistent GPU state, which allows us to reduce the number of render nodes we have to process and then scale the work to multiple threads. Commands are passed to our render thread in a producer-consumer model where the graphics device backend can consume the commands in a platform-specific way. Some backends directly submit the commands, others use native graphics jobs to process the command stream. This render thread is allowed to overlap the next frame, so the main thread can start processing right when all the submits are completed. I've talked quite a while now about how we build and organize rendering with an SRP layer at Unity, but it doesn't solve all of our issues that we wish to address in our rendering stack. You may remember that the SRP is a batch processing system working on groups of nodes rather than individual nodes. Our next step is to go much wider. I'll pass over to Sebastian to talk about the architecture we have in this area and the decisions we are currently making. Thank you.
Hi, I'm Sebastian Aaltonen. I'm working as principal graphics engineer at Unity. Today, I'm going to be talking about our hybrid DOTS SRP rendering architecture, which is combining these two new pieces of technology, DOTS and SRPs, together. This new technology no longer supports the old built-in rendering pipeline. Let's start with the reasons why we need changes in our technologies. Modern games are becoming more realistic and demands towards larger and more dense worlds are growing. Render needs to efficiently push lots of draw calls and data streaming needs to be highly efficient. The growth in CPU core count means more simulation and more dynamic behavior. Our data structures and threading models need to handle this efficiently. Games tend to have a high degree of temporal coherency. Even though we have more CPU cores to drive simulation, the increases in density, world size, and draw distances mean that the huge majority of drawn objects will remain unchanged from the previous frame. Modern renderers are also rendering the same object multiple times to multiple render passes every frame. We don't want to upload the same object data again and again for every draw call. The DOTS architecture is the cornerstone of Unity's new improved runtime. Let's delve into the reasons why we chose to build DOTS and what it provides us. Unity is using classic object-oriented data model with deep class hierarchies. This kind of data model is great for content authoring and prototyping, but the runtime performance is lacking. Game objects form a complex pointer soup style data structure where it's hard to restrict access. Fat object and pointer chasing adds a lot of cache misses, and virtual calls make it difficult to reason about data processing. It's hard to multi-thread a data model like this safely, so we can't simply scale up the performance by adding more threads. In order to meet the increasing demands of high-end developers, we must find a better data model for the runtime, designed ground up for modern multi-core CPU architectures. Our solution for meeting this runtime performance goal is DOTS. This is a brand new data-oriented tech stack with a new data model, new threading model, and a new compiler. The DOTS ECS forms the foundation of the new data model. It separates components into chunks of linear data based on their archetype and offers an efficient query interface for processing data safely without concerns of data races. The DOTS job system provides fine-grained task paralysis, scaling to all of the available CPU cores on mobile console and desktop hardware. The burst compiler is a new C# auto-vectorized compiler covering a C99 subset of the C# language. DOT is using a non-destructive data conversion process. Authoring is done using the existing assets and game object tools. Iterative conversion from game objects to DOTS ECS is running in the editor in the background, resulting in optimal runtime data layout and performance, while retaining good iteration time and improving editor responsiveness in large scenes. Now let's shift our focus on the graphics side. I will introduce the graphics technologies we use to meet our performance needs. The SRP Batcher was originally released 2 years ago. The goal was to improve the performance of game object rendering with scriptable render pipelines. This was achieved by two means. First, the SRP batcher is building batches of compatible renders to avoid costly shader changes. And second, the SRP batcher is fully separating the material storage and upload from the high-frequency draw loop. The material data is now persistent in GPU memory and uploaded only when changed. These changes make the game object rendering much faster. In the best cases, we see the total frame time to drop to roughly half of the original SRP batcher. This result gave us increased motivation in finding more performance wins by making more GPU data persistent. We have a new prototype with persistent descriptor sets, which is a new feature in Vulkan Data Text and Metal, albeit the naming varies across APIs. This feature allows us to persistently bind all the descriptors together ahead of time and change the material at runtime with a single low-level API call, resulting in a big performance win. Now, let's talk about the DOTS hybrid renderer. The hybrid renderer technology is a new technology that connects DOTS ECS to the Unity's existing rendering architecture. This allows us to keep the existing graphics authoring tools in place while replacing the runtime with a faster one. The SRP frontend stays the same. We use the existing assets and big parts of the existing graphics backend. The SRP batcher exposes a new C# API for submitting the batches and the draw data from external sources. The hybrid renderer collects the DOTS ECS data, builds persistent batches, and calculates the visibility. Draws and batches go to the SRP batcher, while the ECS data is uploaded directly to GPU, avoiding the slow existing data pipelines. Most of the hybrid renderer code is written as burst C# jobs, enabling SIMD code gen and allowing it to scale perfectly to any amount of cores. Now let's dig deeper into the DOTS ECS data model to get a good understanding how the CPU data is processed. And let's start with the DOTS conversion process. We convert existing authoring game object data to efficient runtime data layout based on DOTS ECS entities and components. Conversion is non-destructive and iterative. It runs in the editor as a background process. Subscenes in the editor can be open or closed for editing. Closed subscenes are converted to ECS entities, while open subscenes are represented solely as game objects. This keeps the editor responsive when written large game words. The component set conversion scripts are written in C#. The user can write their own conversion script for their own custom game component sets. Assets are not converted. The asset references are simply copied to the DOTS components. DOTS ECS has a chunk-based data model. Entities are split to archetypes based on their component set. Entities with different archetype are split to different chunks. DOTS use fixed size 16 kilobyte chunks. This makes memory allocation trivial. Each DOTS chunk contains an array per component. Each array in the chunk has the same amount of elements, each matching the same entity. There's a special array for entity identifiers that is present in every chunk. The combined size of the arrays is always 16 kilobytes minus metadata and alignment, of course. In the left-hand side, you see a chunk of archetype A. This archetype contains the following components: local to world matrix, material color override component, and the mesh renderer share component, which is shared between all entities in this chunk. On the right-hand side, you see a chunk of archetype B. This archetype has some additional components related to animation, gameplay, and physics. Chunks of this archetype fit less entities as the component takes more space. The main way of processing DOTS ECS data is ECS queries. DOTS query is an inner joined query over a set of components. Each archetype is matched against the query component set. If the archetype contains all of the query component, all chunks of that archetype are included in the query. The query processes through the selected component arrays of each chunk. Only the components in the query are touched. Other unrelated data is not touched, resulting in almost perfect cache line efficiency. Since the chunk component arrays are contiguous, the burst compiler can efficiently auto-vectorize the inner iteration loops. Change tracking is a hard problem to solve efficiently and robustly. It's easier to make it a responsibility of the content creators. They define what is static and what is dynamic. Unity, however, doesn't want to add complexity to content creators. Fortunately, the DOTS architecture has a nice solution for this problem. DOTS queries define read and write access properties to each component included in the query. This helps with scheduling, as multiple reads of the same data are race-free and can be executed concurrently. Since the write access is tracked explicitly and misuse is guarded by the compiler, we know which component arrays in each chunk were potentially modified. To implement a free data version tracking system, we add a version number to each component array in the chunk. When write access is requested, the array version number is pumped to the global version counter, which is a monotonically increasing integer. Systems store previously seen global version counter value. This value can be used as a version change filter in the future queries to limit the query over chunks that have changed since the system saw them previously. This change tracking system is more robust than dirty flags and doesn't require any additional bookkeeping. We rely heavily on DOTS change tracking in the hybrid rendering. And now that you understand the basics of the DOTS data model, let's discuss about the hybrid renderer. And let's start with the user-facing frontend first. Unity is all about easy abstractions to the user. Our goal is to make setting up shared data as simple as possible while retaining high performance and data persistence. The user simply adds a matter property attribute in front of their easiest component struct, and we mirror the component in GPU memory and automatically keep the GPU data up to date. There is nothing else the user really needs to know. For advanced users, we also offer an API for manually registering the GPU visible components. This is convenient when you want to enable GPU access of components from external libraries and you don't want to change their source code. DOTS has a custom type manager implementation that provides a subset of C# reflection features. Instead of the slow C# type and string classes, it uses integer identifiers. We only use reflection as startup to avoid any additional runtime costs. To make the easiest data accessible in shaders, we extend the existing Unity HLSL GPU instance in macros. This is a small change in the macro ecosystem. ShaderGraph supports new code gen with these new macros for all input properties. You simply select hybrid instance in the drop-down menu. All existing Unity's built-in shader inputs and most of the built-in URP and HTRP shader inputs are now compatible with DOTS easiest instance data sources. And that's it for the front end. Now let's talk about how the easiest component mirroring the GPU is actually implemented. Let's go back to our analysis about temporal coherency and the SRP patcher. We noticed that GPU persistent data is giving us big performance wins. Instead of rebuilding the instance data for each row call and sending it to GPU memory, we allocate persistent GPU memory for each GPU visible ECS component. We use large byte address buffers to store the ECS data in GPU side. Each ECS chunk belonging to the same DOTS archetype has identical data layout by definition. We introduce a new concept called graphics archetype. Graphic archetype is a subset of the DOTS archetype. It's the set of GPU visible components. Each entity belonging to the same graphics archetype has the same GPU data layout. Thus, we can store them as uncontiguous lockstep arrays, one for each component, suballocated from the byte address buffer. This makes data access calculation trivial and shared. I will now explain how the data update from CPU GPU works. If you remember how the DOTS version tracking works, it's easy to guess how we manage the component delta update from CPU to GPU. We do a query over all the graphics components. In the query for each chunk, we compare each component array version number with the previous frame's global version counter stored in the uploading system. If the version number is larger, we know that somebody has modified the data since we last uploaded it. The query job writes a simple command stream containing source and destination data offsets for each segment of data. Then we run a following job with access to map GPU upload heap pointer. It copies the actual data arrays from the modified chunks to the GPU visible memory. All of these jobs are best compiled and scaled to all of the CPU cores. The second step of the data upload process is to go through the linear upload heap data array and scatter the modifications around the large byte address buffers containing the mirrored ECS data on the GPU. We execute this step using a compute chair. The compute chair reads the simple command stream containing the copy source and destination addresses and used wave-wide loops to efficiently copy the data. In some cases, we prefer to have different GPU data layout. For example, 4 times 3 matrices save 25% of memory and bandwidth, compared to 4x4 matrices. Half flows are also preferable for many GPU data. Our compute shader supports data conversions, and we also handle some special cases like inverse matrix calculation and previous matrix double buffering. This is very nice since ALU work is practically free in our compute shader since it's bandwidth bound. As the data amplification happens in GPU side, our approach significantly reduces the CPU to GPU bandwidth cost. Now let's talk about the way the shader is accessing the data. Traditional GPU instance has known issues. The author of the shader needs to define a hard-coded set of properties that can be overridden per instance, while other properties come from the material. If this set is too large, you end up replicating matter default values all over the GPU memory. If the set is too small, the artists feel restricted and can't deliver the content variants they want, or they use more materials, reducing the batching efficiency. Compiling multiple shader variants of different data layers is a solution to this problem, but most of us are already dying under the combinational explosion, so this path is a no-go. We are creating a metadata constant buffer for each graphics archetype material combination. This contains the start offsets of each shared property data stream. We steal the high bit of the offset of the stripe mask. This way, we can force all instances to read from the same shared memory location instead of reading from contiguous memory addresses. This allows us to store non-overridden material data as a single value instead of replicating it per instance, saving a lot of GPU memory. Our address calculation code costs 2 extra ALU instructions. We are using arithmetic shift to replicate the mask bit and binary AND to mask the instance ID. Metadata is a scalar register, so it's practically free. There is no added vector register pressure. And now let's look at the performance. Here we are comparing the new GPU persistent data model against an older constant buffer-based data model. Both versions are using .ECS. Our new data model sidesteps the slow main data path. We write instance data directly to GPU upload heap from burst jobs. This avoids the instance data setup cost for the HTRP software command buffer, recording, and playback. We see roughly 10x to 30x increases in throughput. If stress testing runs around 6 times faster with the new data model. However, this is perfectly batched, seen with no game logic, so it represents the best case scenario. We do, however, update every entity transform matrix and override color every frame, demonstrating the power of our new partial delta update mechanism. If you want to see the numbers against the game objects, the situation is even more clear. I just included a number for reference, and the throughput difference is over 60x. So that's a big difference.
So if we look back at our principles from the beginning, how did we do with our architecture? And where do we go to next? We've successfully built 2 different rendering stacks based on the SRP architecture, which are flexible and powerful enough to continue to unlock creativity in people that choose to use or modify Unity. We've had numerous games ship successfully in our render pipelines, and more are shipping in the coming years. We've also had success stories on enabling developers ship games building their own custom pipelines. The SRP layer and tooling enables users and pipeline developers alike to have access to the full platform range that we support at both the low level for tuning and higher level scaffolded APIs, providing a pathway for performant scalable rendering. We continue to invest into this to keep improving our scalability. Next, we're building easy workflows for sharing content across render pipelines. Some assets can already target multiple render pipelines, such as SIGGRAPH, for example. Next, we're working on adding support for single cross-RP projects, settings, materials, lights, and more. URP and HDRP show significantly faster performance versus built-in render pipeline on CPU and GPU, and Hybrid.SRP is delivering further drastic performance improvements. With Hybrid, we're able to build a new runtime, solving the performance issues without having to rebuild everything from scratch. Next, we're going to invest further into lower level layer improvements, calling, DirectX, Vulkan, ray tracing, advanced features such as VRS and mesh shaders, and continue optimizing and evolving each pipeline. Developing in the C# and shader combo has proven to be a win for iteration speed. Additionally, developing in a modular fashion in the SRP land has also been a bonus. Yet to try to truly great iteration speed, we need to tackle the problem of shader variants, which, with every option added to each pipeline, continue to grow. That's an area we're going to dig deeper architecturally into next. Rebuilding the render architecture in a living game engine with many customers can be a complex effort. We learned valuable lessons about evolving our ecosystem through the architectural changes, from creating smooth upgrades to our customers to the new architecture, to making it easy for the ecosystem to target the full gamut of our pipelines. One takeaway is that while it's clear that the interface's stability is beneficial, stability of the data interfaces is more important. By having stable data interfaces, we can run the same content on different rendering backends. The other important aspect we've lived through is that for third-party engines like ours, sunsetting architecture is a very long journey, depending on how widely adopted it may be. So at the moment, all of the pipelines are available in the engine as we have a lot of production successfully continue to ship on built-in render pipeline. Overall, we feel we've achieved our goals and learned a ton of great lessons along the way, and we're hardly done. We wanted to express our thanks to the Unity Graphics and Platforms team for helping us build this architecture, as well as to Ali, Matthew, Philippe, Sebastian, Aris, and Pierre for various help in the presentation. The feedback that Steve, Angela, Michael, and Peter Pike have provided helped our presentation tremendously. Thank you all so much. And we also want to thank Ali, David, Leo, Julien, Lance, Leaf, and Heather for all of their help with the video production of this presentation. Last but not least, Unity continues hiring graphics researchers, developers, tech artists, and more worldwide. If you found our architecture interesting, come join us. Help us evolve it and improve it further. We're also hiring principal rendering engineers for the Graphics Innovation Group. Come help us invent new techniques. Thank you all for listening to our talks.